Okay, good afternoon. Good afternoon, I should say. What I want to look at purely as information is to provide you some information in regards to resistors. Now, a number of you are presently probably doing resistors at the moment, but what I want to go through is bear in mind, remembering Ohm's law, okay? The resistor's current I in amps is equal to the resistor's voltage V in volts. Now remember that in a series circuit the applied voltage will be divided across each resistor, and it is important that you remember that, and of course that will be found by V equals I times R. Okay. Now let me just go into here. Now remember this formula, I equals V over R. Okay? And all it is saying here is that the resistor's current I in amps is equal to the resistor's voltage V in volts divided by the resistance R in ohms. And that is what we're looking at here. Okay? Now, with resistance in itself comes power, and we need to look at what power is dissipated in a resistor. That means lost in a resistor. And here the resistor's power consumption, P in watts, W, is equal to the resistor's current I in amps, A, times the resistor's voltage V in volts. So you can see here, power equals I times V, or if you like, P equals V times I, as I like to refer to it for my own self. But bear in mind that that is still, either way, it will still give you the power result. Okay? Now, the resistor's power consumption, again P in watts, is equal to the square value of the resistor's current I in amps. So here we're looking at another formula which we can use to find power. So here we have P equals I squared times R. And that simply means that if I was 2 amps, then you would times 2 times 2, which would give you 4, times the resistance value to give you your power value. Okay? Now the resistor's power consumption P in watts, W, is equal to the square value of the resistor's voltage V in volts divided by the resistor's resistance R in ohms. Here again, what we have here is P equals V squared over R. So here we're looking at P equals V squared divided by R. Okay? So keep that in mind. And all we're showing you here now is resistors connected in parallel. Now some of you would have been drawing some diagrams for me the other day as well in regards to the handouts I gave you and we worked on. Okay? So again, resistors in parallel. Now to find the total resistance in parallel, we need to do resistance of resistors in parallel, R total is given by 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R to the N. Now R to the N simply means any number of resistors in parallel. But remember that when you look at this here, these are referred to as reciprocals. Okay? So the value of these resistance will be as a reciprocal. We would normally invert the left hand side. Now remember also, if we invert the left hand side, it will then just be RT total equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R to the N. Okay? But if we invert the left hand side, we must also invert the right hand side at the end of the calculations. So bear that in mind. And some of you would have done this in class previously already. Excuse me. And here we have resistors in series. Again, 1, R1, R2, R3. There are 3 resistors in series here. Okay? And the total equivalent resistance is simply RT would be equal to R1 plus R2 plus R3 plus R to the N, any number of resistors in series. Okay. Now, so when you add resistors in series, total resistance is increased. But bear in mind that when you add resistors in parallel, the tendency often, the value of resistance is decreased. Okay? Now, here we're looking at the materials. R in ohms of a resistor is equal to resistivity rho. Now, we spoke about rho, R equals rho L over A. And that's a symbol for rho. It simply refers to the resistivity of given materials, okay, times the resistor's length in meters, divided by the resistor's cross-sectional area, A in square meters. So here we have R equals rho L over A. So it's R equals rho. Now that will be the resistivity given to you of a given material times the length of the material, whether it be copper, aluminium, etc., divided by its cross-sectional area. That will be the cross-sectional area A. Okay? Now, all I'm going to bring up here is show you the certain symbols. Now, the IEE Institute of Electronics Engineers had their own symbol at one time, which is the IEE regs, as you may know it now. But again, be aware of the different symbols being used, and it's quite possible now that I believe they've now become one, and that's now the standard symbol for a resistor. Okay? But I may be wrong. Again, there are changes happening all the time, and we still don't know what's going to happen or what effect the Brexit criteria will have on the IE regs. But we'll wait and see what happens. Let me just go back to make sure we got it all in, okay? Now, with this color code, that takes a little bit of practice, but I'm not going to dwell on that too much. My main concern here was the calculation of resistors in series and parallel. Okay, that was my main issue. But showing you how calculation of a value of a resistor using the color coding may not be detrimental in any way, and could be beneficial. But I will leave that little bit for you to sort out for yourselves. I can't do everything for you now, can I? And here we have pull-up resistor and pull-down resistor. And what we're saying here in regards to a pull-up resistor, in digital circuits, pull-up resistors is a regular resistor that is connected to the high voltage supply, example 5 volts or 12 volts, and sets the input or output level of a device to 1. The pull-up resistor set the level to 1. When the input-output is disconnected, when the input-output is connected, the level determined by the device and overrides the pull-up resistor. So it just sets it at the level whether it's plugged in or unplugged to a given ratio of 1, assuming a status for when it's ready to be plugged back in again overall. The pull-down resistor will hold it at a 0 voltage until again it has been plugged in or unplugged. In digital circuits, pull-down resistor is a regular resistor that is connected to the ground, not volts, and sets the input or output level of a device to 0. The pull-down resistor sets the level to 0 when the input-output is disconnected. When the input-output is connected, either way, it sets it at that level. Now, these are useful for means of controlling devices, so forth. Okay, and you will find actually in due course you will come across some of these yourselves. Okay, right, I'm going to stop there now. Thank you for your time. Have a good day. Bye bye.